into 14 through to 17, except I'm not going to do 17. I don't like conceptual questions. If your teacher's big on conceptual class questions, go over it in class. But I'm here to show you how to solve the numerical ones, and even ones like this, which are sort of algebraic. So keep in mind we're in the quotient section, so a lot of these are always going to be about using the quotient rule. But at the end of this whole section, if you have time, I want to point something out. Okay, it's fairly important, and that's about understanding and why we're here. Because if you're just plugging numbers into preset boxes and holes, and suddenly somebody rearranges those boxes on you and you don't know where to drop those numbers anymore, well, what's the point? You're not really doing math. You're just doing, I don't know, data entry, pretty much. So this one is looking, and it's a very similar question. The graph is this, but we're missing A, which is a number, and B is a number. So whenever you see this, don't mistake your A and B as suddenly new coordinates on the Cartesian graph. X and Y are the only coordinates right now. Eventually we're going to be getting into Z's on a Cartesian graph, and everything else are numbers. Everything else is numbers. Okay? And this has a horizontal tangent line at 2 minus 1, which means it's going to have a slope of 0 at that point. So that means if we find the tangent formula for this, it's going to be equal to 0 at that point, which means if we find it for that, we can plug in that point. But as I've said a few times, and this is really key to math, is if you are missing two variables, how many variables are we missing here? We're missing A and B, that's 2. If you're missing two variables, you need minimum 2 equations to find those. In other words, you need 2 various equations that show A plus B is equal to something in order to solve A and then to solve for B. And this one will demonstrate it. Okay, so the first equation, we know that the f prime of x of this is equal to 0 when x is 2 and y is minus 1. That's really important. Okay? It's important for two of these missing equations. Okay? So that means if I find the derivative of this and plug in 2 for all the x's, it's going to be equal to 0. So I can sort of come up with an a plus b equation. Let's start with that one. Okay, so we're going to start with the quotient rule. And the other one is tough to see unless you're experienced. So we're going to start with the quotient rule. Okay, so that's the first thing we learned. By the way, it then asks you to verify it. Use Desmos. I don't know if people are still using graphing calculators. This book was printed like 15 years ago. People are going to be sitting with a computer, but who knows, maybe people are using graphing calculators. So that means you might say, well, I can't use the quotient rule because I have 2 things. And technically you could just leave it like that, and I can show you a way to do that. And it wouldn't be too bad to leave it like that. But for most students, the easiest thing to do is expand that. That's what the expansion is. And now, all of a sudden, you have it. You have a single polynomial to represent those 2 polynomials. Okay, and that's probably the easiest way for us to do that. So let's go through our list. What's our f of x? Just going to make this a tiny bit smaller and a tiny bit less obnoxious. What's our f of x? It's equal to ax plus b. It's up top. It's the numerator of this whole thing. And what's our g of x? Oh, sorry. Let's reassign this and call this not f of x, but we're going to call this for now h of x, just so we don't get confused. So we're going to call that h of x. So what's our g of x? Well, our g of x is that thing down below. But I said for this situation, let's just expand it. So we're going to get it equal to x squared, which I have to put in later, minus 5x plus 4. Okay, so I'll just go to grab the square from there. I'll steal u. Alright, there we go. good enough. So that means what's our f prime? You might say, well, I can't solve it because I don't have information. But I just told you that b represents a number. And when you take a derivative of a number, it's 0. So that b is insignificant to the derivative. The derivative of ax, that's ax to the power of 1. So that means the 1 to the x comes down in front of the a, and then becomes a 0, and the x becomes 1. So that means the derivative of this is just a. So that's one thing you got to be aware of. That's just a number. For instance, if this said 5x plus 7 up here, the derivative would just be 5. In this case, that represents the number in front of x, and that's the number in front of x. Good to know, right? That's just a number. What about the derivative of the bottom? Well, now that we've resolved it, right, we can say the derivative of the bottom is 2x. Again, if you're slow on these, you need to go back and really study the other stuff more. That's way more important than this. So that's the derivative of that. Let's put it all in brackets. So we can partially complete this. So that's what I'm going to do. I'm going to drag this equation down. And then wherever I see f of x, I'm going to put in this equation. And wherever I see g prime of x, I'm going to put in this equation. And that's true for math no matter what. If you make something equal to something else, you can replace it. And I'm also going to put g of x, well, that's g prime of x. I'm also going to put g of x down here, squared. And it's also going to go over here, and it's going to multiply the prime of x, which we've determined as a. Now, don't you remember in the beginning we said that this equation, which by the way, and let's change it to the h prime. The h prime of this equation is going to be equal when this x is equal to 2. Well, this is the h prime equation now. That's what this gives us. That's the h prime equation. Well, we just said it was equal to 0. What was the rule of math? When I find something that's equal to something else, I can replace it anytime I want, over, back, and forth. Well, they also gave us when this occurs, this is 0 when x is 2, which means everywhere I see x, I can put a 2. That's 5 times 2. Good thing it's in red. That's a times 2. That's 2 times 2. That's 5 times 2. That's 2 squared. So some of this, like the bottom, I can solve, right? What's 2 squared? 4. What's 5 times 2? Minus 10. It's minus 5 times 2. And what's plus 4? Boom. 4 plus 4 minus 10. That's all minus 2. And what's minus 2 squared? 4. Wow. Pretty much annihilated the bottom into 4. Up here, we can only solve what's in the bracket. We just have an a multiplying. What's 2 squared? 4. Minus 10. Plus 4. Oh, we got a minus 2 situation again, which makes sense because that was g of x twice. So we essentially have minus 2 times a. If we rearrange it, I like to always have my numbers first. We actually have minus 2. Would have been nice if I kept a version of that. Minus 2a. And remember that it's minus. So I've got to just do this, get rid of this, and just put a nice old minus in front of it. Okay, what about over here? Well, we got to use the first. Let's solve this 2 times 2 thing. We got 4 minus 5, so we got minus 1. And always keep in mind that there's technically a great big square bracket here. Now, how do I know that? Because this over here is an order of operations. I must multiply this before I apply that. You might say, well, you told me this is minus 1 times all that. Yeah, fair enough. I could apply the minus 1 first to these, and then I have to apply to that anyway. Why not just solve this first, then apply the minus to everything? So that means I have an a times minus a2, which is 2a, times minus 1, which is minus 2a, and a plus b times minus 2a, which becomes minus b. So that means in this bracket, I have minus 2a minus b, all multiplied by minus 1. So I'm going to multiply it through, which means I get plus 2a plus b. Huh. Interesting. I don't know if that's accurate. I don't know if I might have done something wrong there. No, I didn't. So, notice this minus 2a plus this 2a. I get b over 4 is equal to 0, which means I can solve my b. Great. I can solve for b, and that means b is equal to 0. Boom. Now, I could go back and solve the whole thing and figure out my a if I wanted to, right? But I also have an equation up here, which is the main equation. It's the h of x, not the h prime of x, the h of x equation. And I already know b is 0, right? And I already know that when x is 2, whoop, when x is 2, what was y? Oh, I got to put a 2 up here as well. What was y? Y was 1. That's on the line. They told me. They told me that when that point occurs, it gives me the tangent 0. Well, that means that is a point on the line. So I can just put it in here. So I have 2a, which is what I like to do instead of a2 sauce. And what's 2 minus 1 down here? 1. And what's 2 minus 4 here? Minus 2. And what's minus 2 times minus 1? Minus 2. And how do I get rid of a divided by 2? Minus 2, I have to multiply it by its reciprocal. So when this side gets multiplied by minus 2 times minus 1, I get a is equal to 2. Therefore, I figured out that a is equal to 2 and b is equal to 0. And if I plug it into the whole formula, which I've kind of destroyed here, but you can still find in your textbook, you will see that it does work. But just to save myself time, I'm going to go up here and notice that it is right. Well, there's the answers to the doc ones. I forgot to verify. It is right there. That's the answer. A is equal to 1. Well, I got a is equal to 2. So I got to go back. So right there, I discovered that I've made a mistake. So probably an arithmetic mistake, which is the most likely. Okay, I'm going to just grab this equation. And I happen to know a bit more about it, actually, that I should have grabbed. Should have grabbed that. The point on it is 2 minus 1. 2 minus 1. And I know b is 0. So I can have this. So that means when x is 2... Oh, no, I got it right. This becomes 1. And this becomes minus 2. And that when it's 2x up here... Oh, what an idiot. I had it as a. So it's 2a up here divided by minus 2 is equal to minus 1. What an idiot. So stupid. So I get a over minus 1 is equal to minus 1. To get rid of this minus 1, I multiply it by its reciprocal on both sides. And I get a is equal to plus 1. Doi. So foolish. It's such an easy mistake. I don't like making easy mistakes. So, 15. We're going to probably use the quotient rule again because this whole chapter is about quotient rules. You can sort of see that, though, it's just a variation of the same thing over and over and over again. It's not necessarily a lot of fun. It's a lot easier if I just kept all of these here so I didn't have to reuse them over and over again. Okay. So we have a concentration of blood after T hours if the drug is taken orally is given by this. When does the concentration reach its maximum value? So good point. Let's figure out a couple things about this. First of all, we're only talking about positive time. So when it's 0 time, the whole thing comes out to 0. So we're talking about a 0.00. And just out of curiosity, when it's 5, when t is equal to 5, okay, I just want to get an idea of what this graph looks like. I get 25 up top, and I get 2 times 25 down 25 squared. 2 times 25 plus out, I get 57 at the top because it's 5 squared here. So we can see that that's probably a turning point, because after that point, this bottom part probably starts taking off. So 5 is 25 over 60, roughly a half. So at 5, we're talking about roughly half. And let's look at something like 3, just to get an idea of what's going on. So when it's 3, it's 15 up top. It's 2 times 9 down here, which is 18 plus 7, 25. So at 3, so at 5, I had like whatever I had. At 3, I have 3 over 5. 3 over 5 at 3. And then let's say 1, I got 5 over 9. So I got like a half. So it's a weird graph. We can see as we get really big, like 1,000,000 over 1,000,000 squared, we're approaching a very small value. So my guess is this whole graph goes up like that other drug one. And then on the left side, it's going to go down like that. So there's a high dose of blood in the right away, especially when we're in the low numbers. The amount of drug is given by concentration, so it's high concentration. They don't tell us. It's usually like milliliters per or milligrams per blood, and then it's per time. So it's high concentration of drugs in the body, and then it diminishes. So it's good to know what this graph does. So I'm going to just take another picture of it. There we go. But clearly, they're asking us a different question. They're saying, when's the maximum? Well, the maximum of this thing is going to happen in 2 points. If it does indeed follow the pattern that I'm saying, like that. I'm pretty sure y is equal to 0 is this, because this is lower than that, which means y is equal to 0 is a horizontal asymptote. Sometimes, when it's like this, it will cross it, but that's always a good estimate. And down below, I can see that there's no value down here that'll create a horizontal asymptote, because I can plug in anything here for t, and it will create a value. So that means we are indeed a continuous graph. There's no horizontal vertical asymptote. And yeah, of course, it does cross y is equal to 0 right there, so that I'm being foolish. Of course it does. But it gives me a good idea of what the graph is. So if I take the derivative of this and make it set to equal 0, I'm going to find 2 spots where the slope of the tangent is 0. I'm going to find that spot, and I'm going to find, since it lets me take a copy, and it won't, and I'm going to find this spot. So that's 2 spots right there. And that's what they're trying to train you to do, is discover on graphs the local max and minimums. It's going to be very useful later on for other graphs, especially cubics. So you're essentially getting into more and more techniques to analyze tougher and tougher graphs. So the concentration of blood of medicine obviously is going to be on this one. So I am looking for only the positive value. Any negative values over here doesn't exist in real time and space. That means the derivative of this equation is going to be equal to 0, and it's only the positive I want. I can set this as f of x. I can set this as g of x. And that means that, and I would want to put brackets around it, and that means the f prime of x is 5, and the g prime of x, or t, I should say, it's t and t, is going to be 4t. And that means I can just take down this equation, and wherever I see things, I can just replace it. So I got my fx here, times my g prime, and I've got my f prime here, and I can place it by my g of x, which I'll also have to put down in the bottom and get rid of its little sombrero. Okay, and that means I have a working equation that equals to 0. And as I've said before, for something that equals to 0, the only thing I know about this is it goes through origin 0, 0. So the denominator doesn't matter, only the numerator does. So I can pretty much forget about that. I know that's a hard concept to understand, but if I have x over 9 When is the whole thing going to be equal to 0? When x is 0, right? If I have x over y, when is the whole thing going to be equal to 0? When x is 0. Y doesn't matter. It's when x is 0. So you can see why the numerator is the thing that matters. So first we have to multiply out the top, and we get 10t cubed plus 35t. So that's that part. Then we have to have minus, big old brackets, 4t times 5t. It's minus. It's 20t squared. And then the minus gets applied. So I'm going to get 5t is that, 4t is that, 5 is that. So I'm going to get 5 times that. It's 10t squared. Ah, look at that. See that? I actually put the f prime over there instead of the f. I shouldn't have been putting the fx there. I should have been putting only the f prime. I make that mistake a lot. So it's only a 5 that goes there. So that means that this isn't 10t cubed, it's 10t squared. Very common mistake, especially when you do sloppy writing like this. And that means that's not 35t, that's 35. And so the denominator doesn't matter, as I said, but this is the actual thing. So I get 10t squared minus 20t squared plus 35. So let me make sure that that's right. 5 times 7 plus 35. There you go. So it's clear that this becomes minus 10t squared. So I get minus 10t squared plus 35. And I set that to equal to 0 because the denominator doesn't matter. And I solve for t squared. Well, minus 10t squared is equal to minus 35 when I subtract it, both sides. And t squared, therefore, is equal to minus 35 divided by minus 10, because I have to multiply it by the reciprocal on both sides. And that means this becomes positive. And what's 35 divided by 10? It's 3.5. And that means t squared, and I'm only concerned about the positive, is equal to 3.5. T squared is equal to 3.5, which means t is equal to the square root of 3.5, which is going to be a roughly, 1.8. And I know there's a plus and minus when I square root both sides here, and that's something to remember. But remember, on the graph, we don't care about the negative concentration. That's why I'm only concerned about the positive. And so technically, this is very accurate like this, and technically you wouldn't change it. But if they wanted it in decimals or set in decimals, you'd then take 3.5 and you would square root it. And you get like 1.8708. 8708. Probably either 1.87 or 1.9. And that means that when the tangent is 0 is going to occur at when t is 1.87 hours. If you want to know the exact hours, you would say that that's 1 hour and 0.87 of minutes. How would you figure that out? Well, this is on a base 10. Minutes is on a base 60. So to figure it out, you have to take the decimal and multiply it by 60. 60. It is indeed 1.87 hours, but if you wanted to figure out the minutes, this is how you would do it. So I get 52 minutes and 0.2. 1 hour, 52 minutes. And now I had a 0.2, and that doesn't mean 20 seconds. It's 0.2 times 60 seconds, because there's 60 seconds in a minute. Well, 0.2 times that is the same as saying 1/5 of that, and that is 12 seconds. So that means after 1 hour, 52 minutes, and 12 seconds, that is the maximum concentration, because that's when the tangent has a horizontal slope. I'm guessing they just say this. Yeah, they do. But keep in mind, my answer is actually how people would speak. You'd never go, doctor, when does this medicine meet its peak? Oh, at 1.87 hours. No, the doctor would say, 1 hour, 52 minutes, and 12 seconds, the medicine will reach its peak concentration. If we're going to get practical, we've got to get practical. Okay, 16 is the last one I'm going to do because I'm not going to do 17. 17 is all conceptual. I'd rather just solve algebra. So I'm just going to not bother. Same questions over and over. From its starting position, S, so that's a distance, is an object that moves in a straight line based on this time. So right away, if I'm going to graph it, I can tell you that it's always positive, right? So, not true, sorry. That it's going to, as this gets bigger, it's going to approach 0. And again, it looks like it's something like this. And then when time is negative, it crosses through. It looks like something like that. And I can tell that because, one, the power up here is less than that, so it's y is equal to 0 is a horizontal asymptote. But also, there's no value of here I can choose that will make the denominator 0, so it does not have a vertical asymptote. But you can also see that when t is 0, s is, or s of 0, is also 0. So you can see that goes for origin. And just as one number, when t is 1, you can see that s of 1 is equal to 1 over 9. And that gives you an idea. And then as t gets bigger, this fraction is going to get smaller and smaller and smaller, faster and faster. It's already small. So it kind of jumps up and then flattens out right away. You can figure out that it jumps up if you take tiny values of t. Like if I take 0.1, this becomes 0.01 plus 8. And that's essentially 1 over 80. Oh, actually, it starts off small, and I think it hits a bump and then flattens, because that's still pretty small. And at 100, yeah, it's over this. 1 over 100, so it gets very small. So it still has a little bump. But anyway, they don't care about that. They say determine when the object changes direction. So they care about this. When's the peak? And when's it going to change directions? And that's an important question for the future. So that means we're going to do the same thing. We're going to set f, and this time I'm not going to put the things. We're going to put f of g there, f of x there. We're going to make this equal to g of x. And we're going to figure out that 2t is the g prime, and we're going to figure out that 1 is the f prime. We're going to know right away that f prime times g prime, or times g of x, minus f of x times g prime all over that squared. So I've done enough times that I've done the quotient rule from memory. And that's sort of the point, is you want to be able to reach this level. Okay? And so essentially we want to figure out when that slope is going to be equal to 0, because that's when it changes directions. Once you hit a peak like that, then you change directions. So obviously, only the top matters. Only the top matters. Okay, so only the top, we get t squared plus 8 minus 2t squared. So we get 8 minus t squared is equal to 0. So that means 8 is equal to t squared, which means when time in seconds is equal to the square root of 8, even though it's plus or minus, we only care about the plus, that's when this changes directions. It hits its maxima. It goes up and then changes directions. And that, if you look at it, square root of 4 times 2 is the same as 2 seconds times square root of 2. That's about 1.41. So that's around 2.8 seconds or so. 2.8 seconds. And let's see what our answer is. Yeah, they gave it even further, 2.83. 2.83. And sure enough, if I'd taken the square root of 8, 2.82, rounds up to 2.83. They're kind of arbitrary about where they're doing their roundups. And in science, usually, if you have a bunch of terms, let's say you have a really long one, 7.894 there, and 3.28 and 3.9, you're usually going to round up to your shortest term because it's the least accurate. So if you make it too valuable in how far it goes in the decimals, it makes your result more inaccurate. So you generally round up to your least accurate term in science. I don't know if anyone's ever told you that. Now, I'm going to close with this. I don't like memorizing. Formulas. And here's why. Even though it's a pain in the butt, let's make that. Yeah, no, let's keep it hard. Even though it's a pain in the butt, you should be able to. What's a good one to do down here? I don't like absolute values. It's the only one I won't really do. Yeah. 9x squared plus 4x plus 3. Even though it's a pain in the butt, you should be able to do this all with a product rule. And you should be able to do it quite easily and logically. And here's how. And I'm just going to keep it in terms of functions. And I'm going to call this function A, and this function B, and this function C, and this function D, just to keep this explanation less mind-blowing. So pretend A, B, C, and D represent those polynomials. Okay? This can be rewritten as this. A times B, which makes sense, times C to the minus 1 times D to the minus 1. Great. The product rule says I have to take this, I have to figure out what this is, times the derivative of that. So I'm just going to call my derivative. I'm going to just box my derivatives. That'll make it easy. Okay. I'll do it like that. And then I'll forget about this because I want to keep it as the original thing. All right. The product rule says also that I will then take all of that and multiply it by this, the derivative of this. So I'm going to put that in a box. Well, obviously, that one's going to be somewhat easy to figure out. Now, this one here is a product again. So that means to figure out the derivative of this one, I have to do a little arrow thing, and I have to say it's going to be b times the derivative of the second one plus, this is just the product rule, plus just the second one times the derivative of b in a box. Great, derivative of b over here, easy to figure out, not a problem. However, I have to apply the product rule here, which says that to find the product of this, I must take this and multiply it by the derivative of that. Finally, it's getting a little bit easier. And add it to that times the derivative of this. Okay. You might go, oh my God, that's mind-blowing. Maybe, but it's all part of math, which means I can replace this entire box, because this entire box here is the thing I did down there, with this. And here's where you would start using colors or whatever. So I just want to get rid of those arrows. So that means I can take all of this and multiply it in brackets times all of this. And the boxes just mean I'm going to be taking the derivative. Okay? And that's great. That means I can get rid of that. Just remember to put a red bracket around it. Good. But keep in mind that this thing represents all of this, which means now I have to take my A and multiply it by all of that. I shouldn't do I'm going to do a blue box out here. Blue bracket. And it's going to be multiplying all of that, which I can kind of squish up a bit, plus that. And remember, the boxes just mean the derivative. And I can just leave the plus there. Great. I've now figured out the derivative of that. You might say, well, no, you haven't. Okay. Keep in mind that this first one is times all of this, plus that, before the blue box is assembled. Whoops. And that is all outside the blue box. So that just means that A is going to be multiplied in all this. Now you can simplify it, for sure. You can notice that B is multiplying all this stuff. You can also notice that there's there's common things. But if you go over here and you now figure out your A prime is 2x, your B prime, which is probably the tough one, is that's the same as x plus x to the 2 plus 4 to the half, which is the same as a half 1 over 2. This down here, square rooted. You get faster and faster at figuring this stuff out, by the way. And then when you figure out your C prime is 6x squared plus 7. And you figure out your D prime is 18x plus 4. You now have equations down here that if you have a value of x, you can figure out the value for A, B, C, D, A prime, B prime, C prime, and D prime. Then you can plug it in everywhere you see these numbers. This does not mean prime. This means that you're going to send it to the denominator. So you want to keep that minus in there, because it also means that once you solve, for your C minus 1s, you have to do a special case for C minus 1. So to solve this C prime, you have to treat it as the minus 1. So you just treat it as the C. Okay? And you treat the D minus 1 as the C. And you treat all of these as the C and the D's. Only the box things matter. Okay? But my point is that once you find them, and the only ones that are tougher are these, once you find them, you can plug that into that expanded thing. And that was just the product rule over and over again. Now, obviously, I use a crazy complicated example, and I don't have much room to write. But if I had a huge, giant sheet of paper and did 5 pages, I can essentially set up a product rule exponent that's very much like the triple one. The triple one says this: when you have 3 products, you're going to add. And all that means is you're going to multiply the 2 products and multiply it by the prime of the third. You're going to take the prime of the other one and multiply it by the product of the other 2. You're going to take the prime of the third and multiply it by the product of the other 2. This keeps extending. It doesn't matter how many products are being multiplied in the numerator. This keeps expanding. You're essentially taking the derivative 1 and multiplying it by the other 3. The tricky part is figuring out the derivatives of these. So to go back and correct one error, this one is actually this, because I sent it to the top. And the rule for this one says that once I solve it, I use the chain rule. So the minus 1 goes here, this becomes minus 2, and I have to multiply it by the derivative of the inside, which is 18x plus 4. then I can take this minus 1 and just run it right through that, or I can just leave it like that. That can be rewritten as this. And that means I have a derivative for this thing, even when it's down here, that I can solve and just plug it into my master equation. I just have to keep track of what are the derivatives in that master equation and what's not. The first step is just to rewrite it as A times B times C times D, and then you have to figure out when you're going to just use the C or when you're going to use the C prime, because it's going to be A prime times B times C times D plus A times B prime times C times D plus A times B times C prime times D plus A times B times C times D prime. It's just keeping track of what are C primes and what are C's, as in terms of like which one's the function and which one's the derivative of the function, and which one has a exponent that eventually will go down to the denominator. But you will be able to figure out all of it easily. You can even put it to the -1 exponent, because the calculator will notice that what that means. And I'd rather you learn how to do that than just follow this rote pattern of plugging things in.